that operate on variables with unbounded domains, such as integers or reals. So these synthesis problems, they bridge the two directions in synthesis, one of which is program synthesis, where the focus is on synthesizing classical programs from input-output relations, plus possibly additional grammars. And the domain of variables there are usually infinite states. But these type of techniques are focused on synthesizing data transformations. In the other line of research, we have reactive synthesis, which is focused on synthesizing finite state controllers from expressive temporal logic specifications, and the main techniques used there are game solving, and the focus is on synthesizing abstract control. So many systems in practice, they need both intricate control that we want to describe using temporal properties and data transformations, namely they work on unbounded variables with unbounded domains. I will briefly cover some of the main techniques for infinite state synthesis from the literature. So the dominant approach is using abstraction and abstraction refinement. So we saw that yesterday in Nir's talk. The key idea there is that the problem is reduced to the finite state case, where kind of the main burden for solving the synthesis problem is on the synthesis techniques for finite state reactive systems, and the kind of data aspect comes through the refinement of this finite abstraction. So another line of work is what I will call a kind of symbolic game solving, which lifts the classical techniques for solving game to operating on symbolic domains that allow us to represent and manipulate infinite sets of states. So I'm not covering here a range of other approaches which are based on constraint solving and other techniques which are usually focused on systems on kind of synthesis problems with restricted classes of objectives such as reachability and safety. So as we saw yesterday in Nir's talk, one of the main challenges for the abstraction-based techniques is finding good abstractions. Before, kind of prior to the work that Nir presented on using transition predicates for refinement, other techniques would fail to terminate on very simple examples. And similarly, with kind of techniques that just naively lift symbolic game-solving algorithms, again, they fail on fairly simple synthesis tasks, where more complicated reasoning for establishing and finding the solution of the game is required. So in this talk, I will cover one approach which we recently introduced, which is a symbolic game solving approach that aims to address the limitation of the prior symbolic techniques for game solving for infinite state games. Then I will talk on how we use. I'll talk about how we use abstraction to actually improve the performance of that method. Before I introduce our approach, let me briefly present the model that we use to represent infinite state games, and also introduce a running example that I will use to illustrate the main ideas of our techniques. So this is an example of a sample collecting robot which kind of receives requests from the environment, how many numbers of samples the robot has to collect. Then it can move to reach the mine location where it can actually collect these samples and then return back to that. It can only return back to the base if enough samples have been collected. Now, for now, it's not necessary to understand the details of the example itself, and we represent infinite state two-player turn-based games using this type of structures where we have a finite set of locations. So in this case, this is base, move, and mine. We have input variables whose values are determined by the environment. In this case, this is this number of requested samples and some other variables A and B that come up here, and we will see them later. And we also have program variables, which are which are used to represent the state of the game. So here we have variables that represent the position of the robot, where it's done, whether it's done with collecting samples, for storing the requested number of samples, and for counting how many samples have been collected. So the edges between the locations are labeled with guards, which label kind of the transitions from locations to these intermediate squares, which essentially kind of are used to just model the step between reading input and deciding on how the variables are updated. So we have guards which can refer to both the input variables and the program variables. For example, from base, if the requested number of samples is positive, then the robot has to transition here and then move to location move. Otherwise, it will stay in location in the base location. Is coming on the next slide. So we have also updates, which are the updates, which are how the program variables are updated. For example, in location move, whatever the state is, the robot, the system can choose either to decrement the position or to increment the position. So we have this model is a two-player game where the environment chooses the values for the input variables and the system chooses the update. So we have a finite a set of these updates, which are essentially, so we have a finite number of choices for the system, but a possibly infinite set of choices for the environment. And the winning conditions in the game are modeled are location-based specifications. For example, reaching some location infinitely often, or reaching a set of locations infinitely often, or in general, also parity conditions defined in terms of the locations. Any questions? Yes?
You have finitely many moves possible for the program.
Yes.
And the environment having infinitely many choices is just values for the variables. It's really not a move, right? As in, it's not computing things. It's just a sample from an infinite set in some sense.
Yes, it's an
domain.
infinite branching in some sense.
So one of the main challenges that we faced when we wanted to do this is tackle the fact that you don't know that the only instruction you can execute is +1. You have to decide what sort of update you want to do, but you're fixing this, which kind of simplifies
so in
the
this
problem.
model, this is fixed. So in general, the model can be generalized to like by introducing primed versions of the variables and having here constraints on the primed versions, or no, so allowing arbitrary updates to the.
So you're saying that the fact that you have this +1, -1 is no simplification in your game. Any other version would have been equally.
So, the simplification that comes here, so from having a finite a set of possible choices, right, we don't have to have an extra quantifier, right? Otherwise, kind of describing the controllable predecessor will have quantifier alternation, right? And now one can replace the quantifier with conjunction or respectively disjunction, depending on the view. And then it also makes things a little bit easier afterwards for extracting programs, right? Because you have to consider the finite set of updates.
And I have more or less basically the same question about knowing about all the variables that the program would use, because coming up with an intermediate variable is kind of one of these, Hail Mary kind of things that, I don't know that I have to invent 3 variables to be able to do this computation. If someone were to tell me, it would be much easier to do this, but it's hard to know how you could kind of invent those out of thin air.
So the result will also have it will have auxiliary variables, so these are the variables that come from the specification essentially. So you can think of that these come from a temporal specification.
Okay, so every variable that is mentioned in the specification would be here.
This is how we specify the synthesis problem, and then so this can be compiled down from a temporal logic specification essentially.
Quick question: what are enough and have samples there? Are they
who controls these are just shortcuts. They're not relevant for now. They will appear. So they're just shortcuts for formulas that are a bit longer and do not fit here. Sorry. So our the task for the game solving procedure is to compute the winning region for the system, or alternatively for the environment. And because we consider variables with unbounded domains, the problem is in general undecidable. Now, the way that we approach it is we kind of lift the classical algorithms for doing symbolic nested fixed, like for doing nested fixed point. So the game using nested fixed point computations, and we represent the sets of states symbolically. So for convenience, I use notation which maps from these locations to formulas that describe the variables of the values of the possible values of the program variables. And one of the kind of main ingredients of these symbolic approaches is computing attractors. So consider here the subtask which requires us to compute from which states the system player can enforce reaching the set of states described like this. So this tells me that I'm either in location base or in location move, and not in location min. So top stands for true, bottom stands for false. Now these shortcuts that I used here become important, and we can see that from location min, in order to get back to location base or move, the system would have to take this transition, which has the guard enough. So enough requires that the number of collected samples is greater or equal than the number of requested samples. And the way that the robot operates in this location mine is determined by these possible transitions and choices, namely if there are enough samples in one of the locations A and B, then the robot can choose from which location to collect samples. Otherwise, it can always collect at least one sample itself. So it's easy to see that under all possible behaviors of the environment, the system can always ensure to increment the value of samples and keeping the value of the requested samples unchanged, unless we have already collected enough samples. Any questions? So the way to compute the attractor is to perform kind of this iterative fixed point computation, where we compute the set of states from which this set of states can be enforceably reached in one step. In this case, this is the set of states where in location mine we have collected sufficiently many samples to satisfy the guard here. In 2 steps, we have to have at least in 2 steps, we can the system can enforce reaching this set if it has at least requested number -1 and so on. Sorry. This computation performed like this would never terminate because it would generate kind of larger and larger sets of states represented symbolically, and this is also the reason for which many of the abstraction techniques do not terminate, because they would refine with kind of generating more and more of these predicates, unless they use the techniques that the approach that Nir presented yesterday. So how do we address this problem? We proposed a technique called attractor acceleration, where the goal is to accelerate this iterative computation by adding at a single step a set of states by extending the attractor at a single step with an infinite set of states. The key ingredient here is a notion we call the acceleration lemma. So this has 3 components, which are formulas. So base and conclusion, they describe sets of states, and step describes a step relation. And such a triple is an acceleration lemma. If whenever we start in a state that belongs to this conclusion set, and we follow a sequence of states that agrees with the step relation, we will end up in the base. So this is some form of ranking argument. Now, how can we use that to accelerate our attractor computation? Well, if we establish that base is included in the part of the attractor that we have already computed, and we establish that the respective player for whom we are computing the attractor can actually enforce this step relation, then we can actually take this conclusion set and add it directly at a single iteration to our attractor. So in our example, this base would correspond to this predicate describing to the set of states where we have collected enough sample. The step relation is actually describing the increase of the number of samples, while the requested number of samples staying the same from one iteration from location mine back to mine. So if the system can enforce this in one step, then it can be iterated until we satisfy this condition. So using that, we can conclude that the system can enforce reaching the target set of states from any state in location mine. And then we will add top to the attractor, which means that this attractor computation will terminate if we do that. Now, finding acceleration lemmas is actually the challenge here. And the way we approach that is we perform these computations using so-called uninterpreted lemmas. So those are represented with uninterpreted functions. We collect constraints that these uninterpreted functions should satisfy. And we use and the grammar and templates and queries to an SMT solvers to find solutions for those. So the challenge is that as the game size increases, those constraints become more and more complex, and also for establishing kind of that the respective player can enforce the step relation, this requires kind of a recursive query to the attractor computation, which means that overall the constraints can become very complicated, and they refer to all the that they can in the worst case refer to all the variables and aspects of the game that are maybe not relevant for the argument that we want to establish. So in the example that I showed you, and we had this very kind of local reasoning for one part of the game structure, and this is actually what our aim is. Namely, we want to pre-compute some localized attractors in what we call kind of small and useful sub-games. And then we want to utilize these cached results when solving the actual global game. So the goal of this is that whenever possible, we want to avoid kind of performing this attractor acceleration, considering the whole game. And also, we want to apply, ideally, apply acceleration at places where it is like parts of the game where this is relevant and useful, and not have attempts that don't lead to actual acceleration. So if I would be able to pre-compute this result, so I would, by kind of solving a game, a reachability game in a sub part of the game, I would compute kind of this result of local acceleration, which looks like this. So this is the lemma that we had before. And what I will cache is this target set, namely that describes the set of states that the system player can enforce to reach, starting from the states in this set of states. And in addition, what we also compute is a set of independent variables. So those are either variables that don't change or that are irrelevant for the argument, which is essential for afterwards applying this, being able to utilize this cached result in a context which is not necessary, which can possibly have different constraints that are not accounted for in the cached computation. So that is all very nice, but where do these small and useful sub-games come from? In order to determine that, we consider sub-games induced by what we call helpful edges. And the idea is to capture the transitions that a player might need to take, and hence the game-solving procedure has to establish that the player can eventually enable their guards. So in our example, that was this guard here, where we used acceleration in order to establish that the system player can enforce eventually satisfying the guard and taking the transition. But this just shifts the problem, right? So from identifying these useful, small and useful subgames to finding these so-called helpful edges, and then this kind of criterion refers to essentially solving the game. So how do we approach that? Well, we use abstraction. And the idea is that we use a finite set of predicates in order to compute two abstract game structures, one in which we over-approximate the system player, in one in which we under-approximate the system player. So essentially, here we over-approximate the environment player. And the predicates that we use, we take them in kind of one approach to find these predicates is to take them from the guards in the game structure that we have. So using this, so with that we arrive at two finite state abstract games, and we can compute under approximations of the winning sets for the system player and the environment player. But then there is this rest of the space where we don't know. And typical abstraction refinement approaches would now try to refine these abstractions in order to actually arrive at the precise result. What we do is we look at the actual over approximation of the set of the winning region for the respective player. For example, here the over approximation of the winning region for the system player computed here, and we want to use this. We want to use this for identifying these helpful edges. So how do we do that? We look at the so-called permissive winning strategy templates introduced by Nantnayak and Schmuck, which represent a potentially infinite set of winning strategies for a player through local edge conditions. Now, these local edge conditions are grouped, so such a template is represented by a set of live groups, a set of co-live edges, and a set of unsafe edges. And they describe a set of strategies that satisfy the following conditions. So for every live group, if the source vertex is visited infinitely often, then some of these edges should be taken infinitely often. For the co-live edges, they should be taken only finitely many times. And the unsafe edges are the ones that take you out of the winning region, and they should never be taken. So we use these local conditions in order to find our potential, so computed in the, so we use these local conditions for the templates computed in the finite abstraction in order to find our helpful edges. And for the helpful edges, we take the edges that belong to a live group or are safe alternatives to co-live edges. So those are good candidates because those are kind of edges that would make progress towards say visiting a Buchy state, or those are the alternatives that have to be taken once we stop taking these edges. And in our example, this transition here corresponds to an edge that belongs to a live group for the system player in the game where we over-approximate the system player. So essentially this corresponds to the transition where like in the abstract game, this corresponds to the transition where the value of this the variable finally becomes greater or equal to the requested to the variable of the request variable, the value of the request variable. Now, to put it all together, given a game and a finite set of predicates, we construct these two abstractions. And for each of them, we compute a strategy template for the over-approximated player. So we are optimistic, and we look at the player to whom we have given more power. From those, we extract our helpful edges, use them to construct these local sub-games. And I will not go into the details of how these games are constructed. Then in those, we compute attractors for certain sets of states that we determine in this construction and that are also based on the edges and the abstraction. And finally, using those cached results, we use the symbolic fixed point-based methods, utilizing whenever possible the results that we have already pre-computed. We have implemented this approach in a prototype tool called RPG Stella, and we compared it to the RPG solver, which is the baseline solver for solving reactive program games. And we also compared to encoding of the synthesis problem to a solver for a fixed point first order logic mu-val. We performed the evaluation on 3 newly introduced set of benchmarks, because on the benchmarks from the literature, the RPG solver performs well. So the tool and the benchmarks are available on Zenodo. As kind of expected, RPG Stella outperforms the pure RPG solve and also mu-val in most cases, except for this one. So we also compare to just pruning, which is just using the abstraction to determine the value of the under approximation that we have. But this, in most cases, this just is not very helpful. So we really need the templates and the helpful edges in order to perform this cached computation of the results. And yeah, so with that, I will have to conclude. So I presented an approach to solving infinite state games where we combine symbolic game solving with abstraction and strategy templates. And we saw that this local attractor pre-computation and caching actually can improve performance. This is still the beginning of this whole line of work. One direction is now exploring different abstraction techniques, also using data flow analysis for reactive program games in order to perform some of these analyses of what are relevant variables in certain parts of the game. And further, our integration of other techniques for computing the acceleration lemma instantiations and also for winning strategy extraction. So thank you, and I'm happy to take questions.
So we're kind of getting late, and I had to put the last speaker between you and lunch to push it. So mark down your questions. We have time in the afternoon to ask all the speakers. Eugenia, why don't you come to give the closing talk for the workshop?